Okay, so now I'm going to start talking about metals, and in particular, the physical properties of metals and what sets them apart. We've learnt that our periodic table is mostly made up of metals. So we're going to actually look at why we like them, why we use them, and why we mine them, which relates to issues investigation. Okay? Why we mine them. As we have established, the electronegativity, the ability to hold on to electrons, is low in metals. They have low electronegativity. The atoms pack close together, all right? When you have all the metals together, they'll pack closely, and the electrons will run free. They're free to roam. So if you had a block, say this was a block of gold, okay, you'd have all the little individual nuclei of the atom packed in nice and tight, positive charges, positive cores, and the electrons, because they're not being held in place quite as well, will just flow from atom to atom in a delocalized, what we call a delocalized cloud, or a sea of electrons between those metal atoms. And this structure gives the physical properties of metals. So if I've got here, if you can imagine all the nuclei lined up and then the electrons just flowing in between. They just flow around. They're not getting passed to form a bond. They're not filling another atom's shell or being donated. They're just being passed around. Because they can't hold on to them very well. So this guy kind of holds on to electrons, but this guy also kind of does, and he pulls one his way and he pulls one that way, and they just fly around. Okay? And that packing, that closeness of those atoms gives rise to its large density. If you're dense, you have more particles in a unit of space, and that makes you heavier. That's why if you pick up, a small bar of iron, it's heavier than a small bar of wood. Metals tend to have large numbers of protons and neutrons in the nucleus, and the atoms are packed closely together. This gives a lot more mass and a high density. Aluminium is a light metal, okay? So it's quite hard as a metal goes. And we use aluminium for aircraft because of its lightness. All right, it's the lightest of those metals. We can't really make aircraft out of lithium or beryllium, and boron is difficult. So we use aluminium, which is a proper metal, and the lightest of those real industrial metals.
What's carbon fiber?
Carbon fiber is small structures of carbons forming 4 bonds with itself to create these large sort of lattices, and it creates these little filaments, okay? Super small filaments, and they kind of can conduct electricity between them, because what they'll do is they'll leave one bond free for the electrons to flow around, makes them conductors, makes them extremely reactive. You can, if you lit them on fire, the surface area, they would explode into CO2 instantaneously, all right? If you pumped it full of oxygen and lit it up, they can act as a bomb. Like I had a small packet here that could have been used like that. Basically, it is an extremely strong, it's like as hard as diamond, you can't break the bonds very easily, and extremely small. So we use it to deliver just nanodrugs, targeted cells. So if you have a targeted cell, you can use a nanotube, get the drugs down there. All different applications. Carbon fiber has been used for stopping bullets. You can use it in windows if you spread it out thinly enough. It's kind of like fiberglass, but with carbon. Okay, just thin. Anyway, carbon's not a metal.
What's lattices again?
Lattice is when you just have repeating units.
Yeah.
Okay? So repeat, like a pattern, a repeating pattern.
Yeah.
So the density is the first property I want you to be aware of. The second property is the conductivity. The conductivity. Because they are free, because those electrons can just, you know, are passed around, that means if you added one electron in one end, it would automatically just push those electrons due to the repulsion all the way along the chain and knock one out at the other end. That's what electricity is. It's just the movement of electrons. So if you allow, okay, if you push electrons in one end of a wire, you just knock them all out on the other end. And you keep doing that, and that's called an electrical current. So they're great conductors of electricity because the electrons aren't bound to any specific atom. They just keep going.
And good conductors of heat.
Great conductors of heat. And that's more to do with the density because they can just pass the energy along. Joel. Quickly, yep. Question, Christoph.
Do they still use copper in computer parts?
Yes, in circuitry, but they mostly want gold. Okay? The reason why is that computers get very hot. They get quite hot, you start to oxidize the copper. It'll start reacting with oxygen. Then it's useless. Okay? So most circuitry now is based on gold, platinum, those kinds of metals that won't react as much. All right? There are old computers that would have used copper. Your batteries, wires would still probably have copper in them. Your speakers would have copper in them. But the actual circuit board itself does not. Now, our NBN, as glorious as it may seem, is still based on copper wiring. All right? And the issue is that it will deteriorate. It will not be there forever. And it's not very quick because it overheats. So, good conductors of electricity. The atoms are close together and the outer electrons are free. The outer electrons are free, I should say. If you add electrons at one end, the electrons are passed from atom to the other end. Really quickly. Copper will do it. Pass it along. Pass along over miles. All right? Thousands of kilometers you can pass electricity over. Providing you've got metals. Non-metals, okay? Remember, non-metals have high electronegativity. They really want to hold on to those electrons, okay? So they don't pass them on. This is why you cannot conduct electricity through non-metals. It's why diamond won't conduct electricity. It's why silicon won't conduct electricity. Now, carbon, there are certain arrangements where it will. We'll get into that later. Remember, I said there's an exception to every rule. But for the most part, sulfur will not conduct. We learnt that, right? You mapped that out. This is why we call these guys insulators. If you don't conduct electricity, you're an insulator. This is why we coat our wires in rubber, so that we can carry them around. If they weren't, we'd be shocking ourselves all the time.
Hey, why, if we go and grab a power line,
Yeah?
why birds?
Because they're not earthed.
So if we jumped and touched it,
If you hang off the power line, you'd probably be fine.
probably.
It's not something I would do. But if the moment you actually touch something else, like the Stobie pole, and the moment you are grounded to the earth, instead of going along the wire, like passing through you and then along the wire, it's going to go past through you and down into the center of the earth, which creates a huge potential difference. And that voltage is what kills you. All right? All of a sudden, it's gone from a state of pure electricity to nothing, so it's just going to rocket through you.
Holding a massive stick up in the air and chasing the birds across
The birds are fine, because it just floats to them and doesn't damage.
You're an idiot. I know.
So we call these insulators or non-conductors if they're non-metal, but metals, they are conductive.
Oh, can we go back for 1 second? 1 second.
Going to go back for 1 second.
Ah, your head's in the way. Well, I can just-
Okay?
How much electricity does it power line?
Be in the 10,000s, wouldn't it?
Yeah, Dad knows, and he said it's
Yeah.
Some
Dad knows because he says it's yeah. Yeah, yeah. It has to go through a transformer and splits.
That's I wish I had like Bumblebee just outside.
An electrical transformer, you.
You never know, like with these new electric cars,
No.
new transformers go like
Okay.
eco-friendly transformers. They're all like electric cars.
Just stop it there. They are great conductors of heat. They are awesome. Who's ever been welding or they've heated something up and then they've touched the other end of where they're welding and burnt themselves? Yeah. It's all a lesson we've all had where we're welding something, we've got that one end that we're heating up and then we go, oh, just move it out. Okay? This is because the heat is immediately conducted along that chain, along that lattice. It's a measure of kinetic energy. If you think about what heat is, it's just vibrations. So if those vibrations are happening at one atom and they're densely compacted, it's going to knock the other atoms start and vibrate. And then the next one and the next one. And if you keep continually agitating those atoms with a lot of heat, you're going to burn yourself. All right? Seatbelt in summer, right? Ow. As you heat a metal, the atoms vibrate faster. And as they are so close together, they pass that vibration along. Yeah.
What about induction?
Sorry?
What about induction?
Induction of heating, you mean refrigeration?
No, like, for example, like an induction cooktop, so you turn it on and it doesn't get hot until you put it down.
That's because it has to conduct electricity. So the reason why that cooktop gets warm when you put the pan on is because it actually completes the circuit. So you'll have one ring,
But
and
how does it pass through, like,
what do you mean?
glass?
The glass itself is also conductive. It should be passing, I think it's got to complete the circuit. If you look at it, there should be something in the glass, was 2
How
points.
does it do it without actually touching? Because induction, heating works like even if
It
say you
probably
had-
creates a contact
say you
surface,
had
a
coil.
transfer surface. So that, I'm not sure.
Yeah, but say you had a coil and you
Yeah.
put a knife inside it without touching the edges, that still heats up the knife.
Sorry, say you had a coil and a,
And a knife, and you put it inside the coil without touching the edges, it still heats the knife.
I know why. Because electrical flow and magnetic flow are connected, right? So the electric flow causes a magnetic flow, which then causes an electric flow in the knife, which heats it up.
I'd have to look into this. I think it's just to do with the fact that you've got a lot of electricity going through a small amount of space, which is just going to heat up the metal. But I'll have to look into it. I assume it's to do with the conductivity.
So I guess it like jumps.
Yeah.
Yeah. If you can create electricity with a magnet, and you can create a magnet with electricity. So
It might just be like an amplifier, like you would with a speaker. Same sort of deal. I don't know. I have to look into it. Now, remember non-metals, just to make sure we're forever looking at the difference. The non-metals are further apart, so the energy is not easily passed on. All right? Think of oxygen as a gas. If you heat up one atom of oxygen, it's going to take it a while for it to bump into another one. Okay, you can still heat up the air, as we know. That's what we use ovens for. We heat up the air to get things warm, and on a warm day, our air is heated up. But that's non-metals. It takes a while to get there. Whereas, metals, they'll do it straight away. They'll heat up. They'll transfer. So again, here we are. All right, heat. And I put my electrons through here as well. Those delocalized electrons show that's how they're arranged. I'll put these notes up on DayMap as well for you to access. Now, they are malleable. And what does malleable mean? they can be beaten into sheets and still retain their structure. They can still be bonded together.
Atoms have feelings.
They probably do. So does the chicken we eat.
What? That's why I'm going vegan.
No. You can beat metals into sheets and they will not break so much. They will be molded. Okay? Malleable and ductile. Who's heard of those terms before? Apart from Craig, who's getting deja vu. So you don't get surf here? Yeah, it's called malleable because you can actually shape it to how you want it without breaking it. Okay? Ductile means you can draw it into a wire. If you've got a big chunk of copper, you can just keep twisting and pounding, twisting, and then you can draw it out into a big, long wire, which we use to conduct electricity. Because they're close 3D packed arrangement, and they've got the electrons flowing in between them, if I actually say I pushed part of the atom across, they would still have the electrons balancing out the charges. They wouldn't repel. Those positive charges won't repel and break. They'll just hold together. All right? It's just like a mass of electrons and protons together. So you just knock it and it just realigns. All right? It'll just realign and make sure it's all evenly spaced and distributed. So if I just hit a sledgehammer, it would just push the positive nuclei, the positive atoms out, and the electrons would just come in and fill in that space to prevent them from repelling each other. Okay? Yep. Question?
If you were to, I know this is a stupid question. If you were to get 2 blocks of the same material,
2 blocks of the same material, yep.
and the same way you push it across, could you take it apart and put it back together?
Yeah, you just apply a bit of heat though. Make sure the electrons are moving. That's what welding is. Smelting is.
How does
Cold welding.
because there's a way to, like, say gold, for example, if you remove the metals.
Did you say cold welding? Or
You can weld
Cold metal.
together.
You can weld the metal together if you... I think that might be because...
So, like, because
Like,
in
it's...
space, like parts of the ship got stuck together at NASA.
Because there was no medium separating them, probably. So what would have happened is instead of, like, because you probably removed that layer of air and oxide, so what would have happened is, see how this is all lined up,
yeah.
they'd have nothing stopping them from rejoining, and they would just do it of their own accord. Okay? So they would just go, oh, hey guys, and then come together, and the electrons would flow through, and the atoms would realign.
You can weld by putting current through two values.
I'll stop there. Those are the physical properties I want you to be aware of for now, and then I'll talk about alloys later.